So we've discussed the topics of power series. We talked about also the convergence of series in general. And all of that work culminates in looking at Taylor and Maclaurin series. Okay? And it's basically the ability to express functions in terms of this power series. Okay? And some functions in higher mathematics are actually defined using their power series. So it's not uncommon to see in real analysis, for example, defining the sines and cosines in terms of power series or the exponential. It's very common to do that. So let's look at the definition. Suppose the function f has derivatives of all orders on an interval centered at the point A. The Taylor series for f centered at A is equal to this, okay, where we could write the Taylor series centered at A this way. And a Taylor series centered at 0 is called the Maclaurin series. So a Maclaurin series is just a special case of the Taylor series. It's just a Taylor series with center at 0. So let's find the Maclaurin series, which is the Taylor series centered at 0, for the following functions, and then find the interval of convergence. So notice the wording. First off, it's asking to find the Maclaurin series and for these given functions. It's not telling you that these functions are actually equal to that Maclaurin series. That's a point that we'll return to towards the end. So we have cosine x, that's equal to f of x, and we're going to represent cosine x. We're going to find its Maclaurin series, okay? So here are the coefficients. We have that from the formula above. Okay, this is how the coefficient looks. And we're evaluating the derivatives at 0 to get the coefficient because we're looking at the Maclaurin series. So we evaluate at the center. And so let's do this. So, all right, we start with f of x. F of 0 is equal to 1, and that's going to help us with the 0th coefficient. We take the derivative, evaluate it at 0, and we get 0. That's going to help us with the first coefficient. Then likewise for the second coefficient, we take the second derivative, evaluate it at 0, we get -1. And third derivative, we get 0. And then at the fourth derivative, something special happens. We get cosine x again, which is where we started. And we get 1. So basically, these derivatives of cosine x are cyclical with a period of 4 derivatives. Okay, and so this allows us to write a general formula. Notice that for the even derivatives, okay, including 0, you have this general formula for the coefficient. And I will note here that 0 factorial equals 1. And for the odd, which are represented by 2k plus 1, you have 0. So the Maclaurin series looks like this, which could be written in this form. For convergence, we use the ratio test, which we're familiar with by now. And something to note here, we had this 2k plus 1. You got to distribute that out. You'll get 2k plus 2, which is 2 integers above 2k. So we write those 2 integers out, the factors explicitly, and we cancel out that 2k factorial. And we end up with this term, which is 0, and so we get convergence along the entire real line. What about for 1 minus x? We're pretty familiar with that. It's the geometric series there, and that's what we're going to expect to find. But let's do it formally. So we're finding the Maclaurin series, so the center is 0. And we get, for the first coefficient, we just evaluate for the 0th coefficient, we evaluate at just a function at 0, and we get 1. And then we take a derivative. We get this. We evaluate it at 0, we get 1. Second derivative, we get this, and we evaluate it, we get at 0 we get 2 factorial. Okay, we get 2, but we're going to express that as 2 factorial because we know where we're going. The third derivative, we get this value. At 0 we get 3 factorial. And likewise, and there's a pattern forming, and it's that at the kth derivative, evaluated at 0, gives you k factorial. And so your coefficients, ck, are going to be k factorial over k factorial, or just 1, which is what we've expected to find. And the interval of convergence there is strictly less x strictly less than 1. We've checked the endpoints several times, and it's pretty intuitive that x equals 1 and x equals -1 will diverge. And so here is our interval of convergence. All right, so why did we find the Maclaurin series of function that we're pretty comfortable with at this point? Well, it's because now we're going to find the Taylor series centered at a equals 5. So up here, the center was at a equals 0. Okay, so Maclaurin series is a Taylor series at center 0. And now we're going to find the expansion at a equals 5 to compare it with what we found before when we expanded at a equals 0. So all right, we take the derivatives. This is how the derivatives look from doing it several times. So our ck will equal this, and we get the following factor. Okay, notice now we're plugging 5 for our x. Okay, we're plugging 5 for our x, which does dramatically change the coefficients. I mean, we now have this alternating term because of the negative that you get from 1 minus 5. And we get this 4 at the bottom. And so here is the Taylor series centered at 5 for 1 over 1 minus x. And we write it out. We could also write out the terms to get an intuition about it. And let's take the limit. Let's take the ratio test. So we do that, and we find that the radius of convergence is 4. So again, radically different than what's before, where the radius of convergence was 1 when the center was 0. So here it's 4. And we get an interval of convergence. Then we will have 5 plus 4 and 5 minus 4. So we'll get an interval of convergence of x between 1 and 9. And we get divergence at endpoints. So we don't include the endpoints there. And that's pretty intuitive to see that at the endpoints you will get a divergence. Okay. So that's moral of this story is that it really does matter where your center is. It changed the radius of a convergence. It changed how the terms look. And we're far away from the asymptote at x equals 1. Okay, when we're at x equals 5. And so we're getting a larger radius of convergence, and this does matter. Well, let's look at another example. Here we have f of x is equal to e to the x, and we want to find the Maclaurin series for f. And we want to find the interval of convergence. And finally, we want to use that Maclaurin series to write out the power series for, or the Maclaurin series for these functions there. Well, the derivative of e to the x is e to the x, so no matter how many derivatives you take, you'll still get e to the x. In the Maclaurin series, we choose center 0, and so all of the derivatives evaluated at 0 will give you 1, and so we get pretty easy coefficient there. And here goes the Maclaurin series for e to the x. Okay, and we use this symbol again because we're being a little more careful in this video with a theorem that will change this symbol to a equals, okay, later on. But so far, we know that it will convert. So let's check the convergence. We'll do the ratio test. We get 0. It's always less than 1 for any x, and so the interval of convergence is minus infinity to infinity. Now, we know that the Maclaurin series will converge on that real line, but what will it converge to? Okay, and you want to say that it'll converge to e to the x, and we'll answer that question in a little bit. For C, now that we have the Maclaurin series, we want to get the Maclaurin series for e to the x. We want to get the Maclaurin series for these. Well, we have a theorem that helped us with, multiplying terms like x to the m, and we could do that straightforwardly here. So we'll just multiply this x to the fourth by the Maclaurin series, and we now have the Maclaurin series for x to the fourth times e to the x. What about e to the minus 2x? Well, that's just composition. We also looked at a theorem with power series for composition, and we'll just, wherever we see x, we plug in negative 2x instead, and we get that. And what about e to the negative x squared? Well, again, wherever we see x in the original Maclaurin series, we plug in negative x squared, because this is just composition, and we get that Maclaurin series. And the interval of convergence for this, it will not change, so it'll be the entire real line. So it's common to encounter terms like that look like this. I mean, we saw with that geometric series with x that we had p is equal to negative 1, and then instead of the plus x here, we had 1 minus x. So terms like this, similar to it at least, come up often. And for a p that's an integer, you could write out the binomial series. Okay, now this is what the binomial series is, and we could even abstract this and look at p's that are not integers. Okay, but we do get terms like this. Okay, and what are those? Those are binomial coefficients, and they're defined for any real number p. Okay, for any real number p in integer k greater than 1. So you could have these binomial coefficients where p could be any real number, and k an integer greater than or equal to 1. And you'll write out p, p minus 1, p minus 2, all the way until you've subtracted up to the k plus 1 term at the end. Okay, so you'll keep increasing this value here until you're subtracting out k minus 1, which is negative k plus 1. Okay, so that's how that works over there. And keep in mind that when k is 0, so p 0, you just get 1 there. All right, well, let's look at this theorem. For real numbers p not equal to 0, the Taylor series for f of x at 1 plus f of x equal to 1 plus x p centered at 0 is the binomial series. Okay, it's more general than up here where we were just looking at values of p that are positive integers. Okay, here it's more general. So here's what we'll get with the binomial coefficients defined more generally up here. And the series converges for x is strictly less than 1, and possibly at endpoints depending on p. If p is non-negative integer, okay, this series terminates and results in a polynomial of degree p. So you're in general going to get an infinite expansion if you don't fulfill the condition that p is non-negative, is a non-negative integer. Okay, so let's look at an example of that. Consider the function f of x is equal to square root of 1 plus x, and right off the bat you could see that this is basically the binomial series with p equals 1/2. Find the first 4 terms of the binomial series for f centered at 0 and approximate the square root of 1.15. So we use the above formula with p equals 1/2. C naught is just 1. Okay, that's the P0 term. That's just 1 there. What about 1/2 1? Well, that's just going to give us just one term there with just P and over 1 factorial. Okay, and we'll get a half there. What about when k equals 2 there? We'll get 1/2 times 1/2 minus 1. Because remember here, we want to go down to, so we'll keep taking, we'll keep subtracting out until we subtract out k minus 1. Okay, and so k minus 1 here is going to be, 1. Okay, so that's that term, negative k plus 1. So negative 2 plus 1. And what about, so we'll get 1/8 there, just doing the arithmetic. And what about C3? Well, 3 there is going to be 3 plus 1, negative 3 plus 1. And so you'll get 2. That you'll keep going down until you get that minus 2. You get 1/16. And so here goes our expansion, our Taylor series for f of x. Okay, which, the Taylor series is called the binomial series when it's centered at 0 for terms like this. And we went up to the third polynomial. All right, we want to approximate square root of 1.15. We already got that 1, so this is just x is equal to 0.15. And notice that the polynomial that we just found here will give us, when we plug 0.15, if it's the 0th polynomial, we get 1. And if we use this polynomial of degree 3, we get this value there. Okay, so we just used the binomial series to approximate square root of 1.15. All right, so we talked about the convergence of the Taylor series, and now we want to talk about not only is it not only is the Taylor series converging, but it's converging to f. Okay, so there's a question of whether the Taylor series converges at all, and then the question is, does it converge to f, which is a stronger statement. Okay, so it not only converges, but we want to see when it will converge to f, and here we have a theorem that will help us. Let f have derivatives of all orders on an open interval I containing a center. The Taylor series for f centered at a converges to f for all x and I if and only if the limit as n goes to infinity of the remainder term is equal to 0 for all x and I. This if and only if means one implies the other. So if you have that the limit of Rn x goes to 0 for all x and I, then you can say that the Taylor series will converge to f. And you could say if the Taylor series converges to f, then this should also be true. Okay. And the remainder term was given over here, okay, by Taylor's theorem that we've looked at before. So this is the remainder term where this c, which we don't know what it is off the bat, we don't have a way to compute it. Nevertheless, we do know that it's between x and a, where we're evaluating the remainder term, and we don't really need to know that c. We just gotta get it bounded. So show that the Maclaurin series for f of x equals e to the x converges to f of x on the interval, on the real line. So the Maclaurin series, we've computed that for e to the x, and the remainder term looks like this. Okay. Now c is between x and a, so the farthest you're going to get away from the center is going to be x, so that's going to be the largest value. Okay. that's going to be the largest value that C could take. It's the farthest away from 0. And so it's going to be x. Okay, so for each x, that's going to be the farthest, that's going to be the largest value that C could be. So we have this bound. And now we got to take the limit not of x, but as n goes to infinity. And so we take the limit as n goes to infinity. X here is treated as a constant. I mean, we could even pull it right out. This e to the x we could pull right out of the limit. And this is a polynomial, and this is a factorial, and we know that that will go to 0. And so we do have this condition. And because we have that condition, we can write an equal sign there. Okay, e to the x is actually equal to its Maclaurin series.